So far, we've learned about 3 different gas laws. We've looked at Boyle's law, Charles' law, and Avogadro's law. We're now going to put all these laws together and see what they combine to give. So, when we combine them all together, we get PV divided by NT equal to R. We can simplify this by moving NT to the other side. We're going to multiply N times T to this side, and then on the other side, also multiply N times T. As we know, whatever's on top and also on bottom cancels out. So, N over T divided N times T divided by N over T cancels out to give us PV equals R times NT. We can rearrange this to give us PV equals nRT, which is known as the ideal gas law. To remember this law, we know that Professor Pivner studied ideal gases. Pivner, ideal gases. So Professor Pivner studied ideal gases. In this case, what does R stand for? We know that P is pressure, V is volume, N stands for the number of moles, and T stands for temperature. R is what we know as the ideal gas constant. The most common R value has units of ATM times liters divided by moles times Kelvin. This constant can change for different units. So, specifically, we'll look at this constant, where pressure is ATM, volume is liters, moles is our unit of mole, and K is for our temperature, standing for Kelvin. Note that sometimes you'll be given temperatures in Celsius that you must convert to Kelvin by adding 273. So this will be our ideal gas constant, 0.0821 moles times liters, or sorry, ATM times liters over mole Kelvin. Here are some other units for R, or other values for R. We see this, it's the same as the previous one, we just added a sig fig. We get liters times kilopascals over moles times Kelvin, that's 8.314. And then the pressure changes once again to millimeters of mercury, which is 62.4. Note, for what we'll do in this class, we'll use 0.08206 or 0.0821. If a container with a volume of 60 liters holds 3.0 moles of an ideal gas at a temperature of 400 Kelvin, what is the pressure inside the container? So remember, the first thing that we're going to do is underline important information. So, first thing I see is volume, 60 liters. Second thing that I see is moles of an ideal gas at a temperature of 400 Kelvin. We'll also see the word pressure, but it doesn't tell us what it is. So this is probably, and I know definitely, our unknown. So I've underlined all the important information. Now let's identify the givens and the unknowns. So again, we have a volume equal to 60 liters. We have moles equal to 3.0 mol, that's the unit for mole. We have temperature equal to 400 Kelvin. And we have an unknown pressure. So, how do we know what law to use? Since we've identified our givens and unknowns, we need to figure out a law that includes all of these things. Notice, we don't have 2 volumes, we don't have 2 temperatures, we don't have 2 pressures, and we don't have 2 number of moles. Since we don't have 2, we're going to use the ideal gas law. Let's recall that Professor Pivner studied ideal gases. So, the ideal gas law, PV equals nRT. Professor Pivner studied ideal gases. Notice, even in the problem, it says ideal gas. Now, we determined the equation. Let's plug in. So, we start off with some unknown pressure times a volume of 60 liters. We know that that equals 3.0 moles times 400 Kelvin times some R value. I forgot the R, so let's include it now. Our R, we have liters, moles, and Kelvin. The one we were told to use most often is 0.0821 liters times ATM over moles times Kelvin. So, in order to put it in the right spot, we're going to include 0.0821 liters times ATM over moles times Kelvin. Then we're going to multiply by our temperature T, which is 400 Kelvin. Next, alright, we need to solve. But before we pick up our calculator, put in the numbers, let's cancel some units. And please notice, we have moles on top and moles on bottom. We know that something over the same thing cancels out. So our moles cancel. Also, we have Kelvin on top and Kelvin on bottom. So those Kelvins cancel out. Now here's a trick. When you have volume on one side of the equation, or a unit on one side of the equation, and a unit on the other side of the equation, both on top or both on bottom, you can cancel them out. So, we'll cancel the liters since it's on top of both sides. Notice, our unknown is pressure. The only unit we have left is ATM. So, ATM, we're good to go. Let's pick up our calculator. So, I'm going to start on this side. I'm going to do 3 times 0.0821 times 400. I get 98.52. I almost forgot my unit. I'm going to continue to include my units. On the opposite side, we have P times 60. To simplify this, we divide by 60, divide by 60, and we get 60 to cancel out, and P equal to 1.642 ATM. And that's our final answer.